Hello everybody, welcome to 3.4 Part B. Our objective today is just the last little piece of this chapter. We're just going to use the second derivative test to find extrema. And to begin this, what we're going to write is really what the second derivative test is in math speak. Right? It says let f be a function such that the f prime of c equals 0 and the second derivative of f exists on an open interval containing these numbers. And if you evaluate your second derivative at these critical numbers, if the second derivative is positive, then you have a relative minimum at that value. If your derivative is negative, your second derivative is negative, then you have a relative max at that value. And here's an important note. If you evaluate your second derivative at that critical number and you get a 0, then you can't use this test to find extrema. You have to use what we learned before, the first derivative test. And since this is another test to find extrema, I want to quickly differentiate for you guys the difference between the second derivative test and the first derivative test. And I'm going to use some bright colors here, and we're going to kind of draw a Venn diagram. Okay, so let's do a big circle here, and let's do a big circle here. Whew. Good thing I'm not a geometry teacher. Okay. So let's talk about the first derivative test. I'm going to say first a D test, and then I'm going to say in blue the second D test. And let's write in black what they both help us find. They both find extrema. We can use to find extrema. And they both use the first derivative at 0. Oh, pardon me. The first derivative, wherever the first derivative is 0, we use those as critical numbers. We use those as the critical numbers for both of these tests, and both tests find extrema. But here are some differences. The first derivative test, we use test numbers from intervals, right? That's what we do with the first derivative test. We kind of look to the left and the right of the critical number when we use the first derivative test. What the second derivative test is a little bit different. We actually use that entire point. So the second derivative test evaluates right at the critical numbers. It doesn't make intervals using the critical numbers. It evaluates the exact critical number that we come up with. And essentially, the second derivative test doesn't look to the left or the right. It looks to see what exactly is happening at that point. And then we determine if there's a relative max or min from that value. So I guess I could have made that smaller, but that's okay. These are the differences, and here's what's the same. So let's start with the second derivative test. Let's jump into an example of that. All right. And our question is going to ask us to find the relative extrema of f of x equals negative 3x to the 5th plus 5x cubed. And it's going to help you guys first, when we're using the second derivative test, to find these extrema. It's important for us to first find the first derivative and then find the second derivative and go from there. So the first derivative here, I would get negative 15x to the 4th plus 15x squared. And my second derivative is going to be negative 60x cubed plus 30x. Okay. And now remember from that definition at the front of this video, at the beginning of this video, we are interested in critical numbers that make our derivative, our first derivative, 0. So what I'm going to do to first find my critical numbers is I'm going to set my first derivative equal to 0. I'm also going to factor at the same time here. So when I factor out a negative 15x squared from the first derivative, I get x squared minus 1 as a factor. And from this, I can determine that the zeros, the critical numbers, are going to be x equals 0, and when x equals positive or negative 1. And now here's what I do with those critical numbers. To use the second derivative test, I take these numbers and I substitute them back into my second derivative. But I'm not just interested in those numbers, I'm interested in the points of my original function. So I'm interested in these x values on my original function as a coordinate. So what I'd like to do is just kind of set up a diagram here. And determine what's going on. Okay. So, what I've got going on so far, we'll call these the points. We'll call this f prime double prime of x, and then we'll determine extrema. So the points I'm going to use are going to be where f is negative 1, where it's 0, and where it is positive 1. And what I'm going to do right now is I'm going to fill in the rest of these points, and I'll explain how I'm getting this. I'm getting the y values here by substituting these back into my f of x, my original function. And when you do that, you can use your calculator. That's just calculator work at this point. We should get the points negative 2, 0, and 2. Okay. Now I'm interested in what's happening here with my second derivative. And when I take these values, when I take negative 1 and I put it into my second derivative, I get a positive value. When I take 0 and I substitute it into my second derivative, I get 0. And when I take 1 and I substitute it into my second derivative, I get a negative number. And so what I've got going on here, if I look at my second derivative test description, it tells me that when my second derivative is positive, I have a minimum at this point. I have a minimum at c, comma, f of c. So I have a minimum here. When my second derivative is less than 0, when my second derivative is negative, I have a maximum at the point c, comma, f of c. Alright, so the second derivative test has been really helpful so far. It's told me I have a minimum at negative 1, negative 2, and that I have a maximum at 1, 2. But it gave me no conclusions at the point 0, 0. So what I can do, that little note told you before, that you need to evaluate what's going on with your function using the first derivative test. If the second derivative test doesn't tell you enough. So here's what we can do. Let me zoom in a little bit more. Okay. I'm going to use my first derivative test. I'm going to pick some intervals that are going to be helpful to me. I know what's happening at negative 1. I know that at negative 1 my first derivative is 0, so that's not helpful. I need to look at the interval instead. We'll call this just the first derivative test. And I'm interested now with my first derivative test looking at, here we go, how about this? Okay. My first derivative test, I'm interested now in the interval from 0 to negative 1, or pardon me, negative 1 to 0, and from 0 to positive 1. I want to know what's happening in those intervals. So some good test numbers might be -1/2 and +1/2. So if I take those numbers and I substitute them into my first derivative, what I get is a positive number and another positive number. So it doesn't really help me that much to see what's happening here. It doesn't help me to use my second derivative test to look at 0, but now when I use my first derivative test, I can see what's happening. I can see that from -1 to 0 and from 0 to 1, my graph is increasing in both of those intervals. So I don't have a max or a min at 0, 0. What we can say is no extrema at 0, 0. And what we can instead conclude is that f has a relative max at 1, 2, and a relative min at -1, -2. And let's graph this real quick to kind of better understand what's going on here. So we get our grapher going, and we're going to graph the original function. We're going to graph -3x to the 5th, and we're going to do plus 5x to the 3rd. And when we graph that, we can see that our conclusion is supported here. Let me zoom in just a little bit closer so you can see just a little bit more clearly what's going on here. All right, here is that point 0, 0. We can see that our graph increases, and kind of takes a break for a second, but continues to increase. So there's no max or min at this point, even though the derivative is 0. Okay. Let's do another example, and then I will leave you alone. All right. Let's answer the question of find the relative extrema. Oh my goodness, you can't see that. There we go. Find the relative extrema of f of x equals 2x to the 4th minus 16x squared. All right, let's get used to the process here. If we're using the second derivative test, the good way to start is to first find your first derivative. And I would get 8x to the 3rd minus 32x for my first derivative. And for my second derivative, my f double prime of x, I would get 24x squared minus 32. All right, again, we're going to identify those critical numbers, and critical numbers for the second derivative test happen where f prime is 0. So I'm going to set it equal to 0, and I'm going to factor at the same time. So I'm going to factor out an 8x. I'm going to get x squared minus 4 as a factor. And now I can clearly see that my critical numbers are going to happen at 0 and at plus or minus 2. So now it's my job to take these x values and create the values, the numbers that are happening on my original function at these x values. So I take these x values and I substitute them back into my original function. And when I do that, I get the following coordinates. -2, -32, 0, 0, and 2, -32. And again, I'm just going to highlight how I came across those values, because I noticed we were kind of asking this question in class. All right. I got these y values from substituting in my critical numbers to f. substituting in critical numbers to f is how I got these y values. All right. Now, let's take these x values, these critical numbers, and let's put them into my second derivative here. And when we do that, when I put a negative 2 into my second derivative, I get a positive value. When I take a 0 and I put it into my second derivative, I get a negative value. And when I take 2, I'm going to get the same value, actually, that I got at this point, given I have a positive exponent, or pardon me, an even exponent. It's not going to change the sign, so it's going to stay positive. Okay. And remember what the second derivative tells us is that if the second derivative is greater than 0, if it's positive at the critical number, then I have a relative minimum, sorry. And if it's negative at a critical number, then I have a maximum. And again, positive means a minimum. So here's how I would report my answer. I would say that f has relative minimums at the points -2, -32, and 2, -32, and has a relative maximum at 0, 0. And I guess we really don't need to say at the point, so you can kind of cross that part out. There we go. Pardon me. Relative minimums at here, and has a relative maximum at 0, 0. Okay, thanks for watching. We'll see you in class tomorrow.